So we're going to look at the first reaction right here. Right, so you can see that the reagents are specific for allylic bromination, MBS, and light. The question is, how many products are we going to get? And this is what's today, 8/19. So how many products are we going to get? And how do we know that? How can we predict that?
You can predict how many products by the number of allylic sites.
Right. And how many allylic sites do we have here? Right. Is this one?
Yes.
And so is this, right?
Yes.
So the number of products is 2 times the allylic sites. All right. So if I got 2 allylic sites, I'm going to get 4 products. We can draw 2 of them right away. Am I right? Because what's the goal of allylic bromination? Keep in mind we're working under this umbrella of um, synthesis of alkyl halides, and so the goal of allylic bromination is to add a bromine at the allylic site. So one of your products for sure is going to look like this. Is that right? Yes, no.
Yes.
All right, and then you're going to have another product that looks like this. Sorry about that. Where you got a bromine on that end.
Dr. Russell, can you check the chat, please?
Yeah, so the allylic site, by definition, is next door to an alkene, right? It's adjacent to a double bond. So those two.
Oh, so it's if it's adjacent to a double bond, that's how you know it's allylic site.
Yes.
Okay, thank you for clarification.
All right. So we're gonna get 2 more products, and I'm gonna draw them, and then we're gonna go back and figure out where they came from by going through the mechanism. All right. So the other allylic product is gonna look like this. Oh, man. We're gonna get a bromine there, and like this.
Not already.
Like that. So we're gonna get all 4
Not
of these.
already. I just got on here. Oh my god. I just got on here. I don't like you.
You're unmuted.
Yeah. You might want to mute before you know. All right. So these are the 4 products. Let's see where they came from. All right, and we're gonna go through this mechanism a step at a time. So what's the first step? And how do we know what type of mechanism it is? What's the clue? Anytime I see light as a part of my reaction, I know that it's a radical mechanism. All right. And if it's a radical mechanism, what do I know about it? How does it go? How does it proceed? Right, you're gonna have an initiation step, and then you're gonna have propagation,
Termination.
followed by termination. Make sure I got enough room. Right, so the initiation step is the formation of that bromine radical from MBS. All right, you shine light on that, you cleave it homolytically, and then you end up with this. Plus that, right? That's a given. So it's the bromine that's coming down into the propagation step. And I say coming down into the propagation step, but it's really kind of all, it's not separated like I'm showing you. I'm just doing that for clarity. What happens in propagation?
Abstraction.
Abstraction of hydrogen. Very good. Thank you. Who was that?
Thank you, Mario.
Thank you. So we're going to start with this substrate, and I'm going to start right here. All right. Plus Br, right, a bromine radical. And then that's going to do abstraction, which happens how? What is the mechanism? Like, what arrows am I putting in?
Isn't the hydrogen and bromine gonna meet?
Like
and
that?
then the other one will go back to the left. Yeah.
I'm going to put that other electron in that CH bond on that carbon. So that's going to give me a new radical that looks like this. Plus HBr. Are you following that? Anybody not see that? This doesn't change. I sent a little refresher video to you the other night to show like what propagation looks like, what initiation looks like. None of that ever changes. The arrows don't change. The substrates might, but the arrows don't. All right. So my other allylic site is down here. I'm gonna write the hydrogens out. No. Yeah, that's right. And the same thing is going to happen. I'm going to take my bromine radical, and I'm going to abstract, right? One of those, all those hydrogens are equivalent, so it doesn't matter which one I take. Which one do you want to take?
Let's take the bottom one.
All right, let's do that. So I'm going to show this cleavage like that. And bromine coming. Notice again, this is very important because on the exam, if you use the wrong arrows, you're going to get docked for that. Since it's radical, all your arrows have to be single-headed. That's something that you can't forget. All right. Anytime you see a single unpaired electron and you're trying to move it, you have to move it with a single-headed arrow. You can't use a double-headed arrow to show the movement of one electron, because this shows the movement of two electrons. All right. So the other radical that I'm going to make in propagation is going to look like this. I'm going to write it out. That's going to be that plus what?
HBr.
Plus HBr. Good. All right. So now the question is, let me add a page right here right quick. Now the question is, where do those other compounds come from, those other two products? If you look at both of those radicals, you can see that they are ripe for doing resonance. We talked about this the other day. Both of these are allylic radicals. Right? If they're both allylic radicals, that means that if it's an allylic radical, you can do resonance on it. You can see right here, you have the radical here on this carbon, and then you have, it's right next door to an alkene. So your donor and your acceptor are right next door to one another. Same thing down here. Here's your radical, and it's next door to a double bond. So both of these are allylic radicals. That means that they're going to rearrange through resonance. So let me just copy these right quick, and we're going to show the resonance forms down below. I don't care about the HBr. Right, so anytime you make that allylic radical, you're going to get a resonance. You're going to have a resonance form. That's possible. So you have to account for that in your mechanism. All right, so let me erase that. I don't need that. And erase these highlights if I can. All right. And let me go down here and do the same thing. And then we're going to show the resonance. All right, so let's take the first one. How do I show, or how do I draw the resonance form for that one? What do I need to do? We just talked about this on Monday, right? And this is something that we also learned in part one, that you got to retain that resonance. You can't like just let it go, let it ooze out onto the pillow. All right. So here you can see that now you're going to have an electron on that carbon. All right, so that's one of them. What about the other one? I need somebody to do this one. You can just annotate. I think the screen sharing and annotation is open or it's turned on. Just need one brave soul. I wish I had some Jeopardy music playing.
Don't we need to move that long pic? Okay.
Right. It's a one electron. It's not a lone pair. So what's the confusion? I just gotta
So can you explain, like, I know we did a residency last class, but can you explain like what's going on? Like you're moving. I know you're saying you need a donor and acceptor, but can you explain like what the arrows is doing exactly?
Can you tell me what resonance is first? Let's start there. And then we'll, because it makes no sense to explain it about why the electron or how the electrons are moving if we don't know why they're moving. So what's the purpose of resonance? Anybody can answer that, by the way. It doesn't just have to be.
Isn't
To
it
get
when-
to the most stable form.
It's
Yeah.
it's a way to stabilize lone pairs, unpaired electrons, right? It's also and how do we do that? What's the term? There's a specific term that we learned. I know everybody didn't take part one from me, so I get that. But when we talked about this in part one, that was a specific term that we learned. Where the stabilization comes from. What was that term? Anybody remember? Starts with a D. Delocalization, right? So the whole purpose of resonance is to delocalize either charge or electron density. So if you got a radical that's next door to an alkene or some other acceptor, then you're able to take that electron and share it over multiple atoms. That's the purpose. And in doing that, what you're doing is taking the electron density from that one carbon with that electron on it and spreading it out over those three atoms in that unit. So that's why we show this the way we show it, right? We show the pi bond breaking in half because now that this electron that was here is now going to be on the carbon on the other end. It's not the same electron, but it's the idea is that you're able to put that single electron somewhere else, which will be here. right? Again, this is something, uh, this is an indispensable skill for part 2, for all organic is resonance, right? So my suggestion would be to review this thoroughly, because you're going to see it from this point forward. A lot of the problems that we do or solve are going to involve resonance and pushing electrons.
Dr. Russell, I have a question.
Go ahead.
So why are there 2 arrows coming out of the double bond right there? Is that just because there's 2 electrons attached to it and we're moving it?
Every bond is made up of 2 electrons.
Right, okay.
So I'm either going to show a double-headed arrow coming off of it, like if I had a allylic anion like this, right? If I move this here, then I got to move this here, right? So anytime I'm breaking a bond, I'm either going to show a double-headed arrow, meaning both electrons are moving, or 2 single-headed arrows, but the idea is the same. I'm moving both electrons in that bond.
Okay, thank you.
Mm-hmm. All right, so these are going to be my 4 radicals formed in propagation. This off here. Can anybody now see? Uh-oh. Where my 4 products are coming from? Right, because if you go back up top, we said we're going to have 4 products. And if you look at all 4 of those products, you can actually see where they came from in terms of what radical they got formed from. All right, so we'll label them. Let me label them. Right, so let's go back down here. We have our radicals. So now each one of these radicals is going to terminate with bromine. That's the termination step. Right, so I'm going to take, let's see if I can paste that again, instead of having to rewrite them. Can't do this on the whiteboard. All right, let me go back. Let me clean this up some. All right, so that's 1. Let me clean this up. All right, so when we talk about the termination step, and we say that they're pairing up with bromine, what do I need to add in order to get to my product? Am I adding HBr? Am I adding BR2? Am I adding MBS? What am I adding?
Is it HBr?
Okay, if I add HBr, is there a free electron on bromine that's able to pair up with that free electron on that carbon? The reason I ask that is that's because that's a common mistake with this reaction, is to try to terminate it with HBr. You can't. You have to terminate it with another radical. All right, so it's got to be here. And it's going to be the same for all four of them. They're going to couple with a bromine. What does I just do? All right. So how am I going to show the coupling?
Are you gonna pair the bromine to that lone pair, that lone electron?
Yes. How am I going to do that? How would you show that happening?
Would you draw an arrow?
Okay. Single or double? Your life
Since
is
it's a
in.
single electron.
We're going to spare your life today. You're sparing your life. I'm joking. Your life wasn't on the line. Right? So that's right. That's those two arrows are what I need to show the formation of a bond through a homogenic process. Right? Hopefully you remember that from part one. Not I don't want to sound like I'm singling you out, but hopefully y'all remember that from part one. When two radicals come together, it's a homogenic bond formation. Right? Just by the same token, when two bonds break, well, when a bond breaks and each atom in the bond takes one electron, like up here, then that's called homolytic. Lytic, just like meaning to cut, genic meaning to form. All right, so you're gonna have the same thing happening in each one of these steps. Boom, here, here, and then here. All right, can somebody draw what the first product is gonna look like? Got a lot of room over there.
Okay, I want to try, but I really don't know what exactly to do or what it looks like. I always had a problem with resonance, and so I would want to try, but please correct me where I'm.
Go ahead and try. This is not resonance. This is just showing bond formation. So go ahead and try. What do you think is happening when I show those two arrows coming together like that? Give me your initial thought on that, and then we're gonna work past it.
Well, you're forming a bond between that electron and the other.
Not the electron, the atom that the electron is on. That's a carbon at vertex, right? So you're making a bond between that carbon and bromine, a sigma bond. So when you draw it on the other side, what is that going to look like? So just go ahead and try to draw it. Just do your best. Okay, I'm with you.
Sorry, it looks a mess. Let me
That's
fix it.
okay. I can decipher it. Just finish it.
Okay.
Yeah. Don't worry about it. Don't worry about the aesthetics. We'll work. We'll fix that. I'm more concerned about just getting the product drawn. It looks neat. You must have changed your pen.
Yeah, I had a straight line thing
I
on it.
got you. I got you. I understand. Come on with it. Okay.
Now this is where I get stuck at.
Don't
So
get stuck. What you see the carbon is highlighted?
yes.
That's where that's where your bond to bromine is going to be. So just draw a line out from that carbon and then put a bromine at the end of it. Right. That's it.
Okay. I thought it was going.
You wanted to sit bromine in that pocket, didn't you?
Yeah.
No, you can't do that. If there's a bond there, you got to show it.
Okay.
If you had drawn bromine here in the pocket, like that, that will mean that that carbon is replaced by that atom, but it's not. We actually make a bond to the atom. So good. That's good. Thank you.
Thank
Anybody
you.
want to do the next one?
Can I ask you the next one?
Go ahead.
Okay.
Please do it. All right. You see, let me scroll out some. You see it, right? What's happening?
Yeah. So the CH2,
Mm-hmm.
that
That's what
carbon,
yeah.
is going to be moved towards the I think that's the third carbon. That's like right there.
Wait a minute now. We're not moving any carbons. We're just
I mean
making a bond.
the bond is
Yeah.
moving
Yeah. The bond is going to be right there at that carbon with that
to this part right here.
electron on it. No, don't touch that. Go to the one. You see the one with the electron at the end? The CH2 right here. That's where you're making your bond. Nothing else is participating.
Okay.
So draw your same structure that you just drew up top, except for the bromine.
And then here, and here.
Now on the carbon down here on the end, right there, I want you to draw a line from that carbon to bromine. Just straight down. Yep. And put a bromine on the end of it. Good. That's the product.
Oh, Dr. Russell.
Yes.
So from the first arrow, well, the arrow on the left, that's where the new product goes, or the new atom goes, right?
Yes.
Okay. Thank you.
Mm-hmm.
So that's it.
That's it.
Okay, so I thought that the bond from the carbon would be something completely different from the bromine, but it's not.
No. You're making a bond between the two atoms. So there's a covalent bond means that they're sharing a pair of electrons. That's all you do.
Okay, that makes sense.
Mm-hmm. What about go ahead. I heard somebody get ready to
So that would have been homogenic, right?
all of it is homogenic because all you're working with is radicals. So anytime you make a bond between two radicals, it's homogenic. If you break a bond between two radicals, then it's homolytic.
Did you want me to erase anything or just keep it on the screen?
No, you can keep it. We're gonna label them. I think I got them in order. So that's A.
Dr. Russell,
That's B. Yes.
can I try the next one?
Yep.
Actually,
Yeah. Please do.
I don't think I can write on the screen.
You got to click annotate.
Yeah, you click view options up top, and then you click annotate.
Yeah, go ahead. Oh, you can print it out. Aren't you on the Wi-Fi?
Oh, I see it. Okay.
Yeah.
Oh, my bad. Sorry, y'all.
Yeah, it's all right.
Okay.
Is this you writing in green? Do you need more room?
Um,
Do I need to scroll up?
could I put it like right here? Oh, I'm not green. I'm the pink.
Okay, yeah, okay. I see. Yeah, you can put it in there. It's fine.
Okay. It would be the same.
That must be the dog again. Yep.
All right.
This is literally the atomic dog because we're working with atoms. Now this, man, I've been thinking about that song all morning. Now I got to go listen to it. Now your dog has a new nickname.
I don't know what dog you are talking about, Dr. Russell.
No, not yours. Somebody else.
Okay.
Somebody's dog is walking on the computer. At least that's what I was told.
Hmm. Okay.
Okay.
And then it goes right here. And
You're doing the third one, right? You're doing this one, right?
Yeah. Yeah.
So your okay. Shouldn't your double bond be on the other side? Shouldn't your double bond be up in?
Yep.
Up in
Yep.
here?
Yep. Let me go back.
That's all right. You can just put it in and put the other methyl group in.
Like
Point it
this?
up. Put the group pointed up on the end carbon.
This?
Yep. And then now come back. You see where the radical is right here?
Yeah.
That's where your bromine, that's where your bond to bromine should be.
Okay, so the bond is always just gonna be
away from the atom.
Right. Okay.
You know, don't feel bad about that. That's a common mistake.
Oops.
Your dog tripping too.
Yeah. Okay. Okay.
All right, got it. That's good. That's good. That's good. All right, who's gonna do the last one? Let me just erase these letters because they're meaningless right now. Anybody? That's good. For both of you who volunteered. That's excellent.
Dr. Russell, I'll do it.
Come on. Right. All we're doing is drawing the termination products.
All right, about to start.
All right. Okay. Okay. Good. Perfect. And you circled it too to make sure we knew.
Yeah.
Well, you tried to circle it.
Yeah.
It's a rough circle, but it's all right. We're gonna take it. All right. Does anybody have any questions about that? I mean, this is not. We're not doing anything, and I say this all the time in part 2. We're not doing anything new. It's the same principles from part 1 that we learned. Did it print? It's the same principles that we learned in part one. We just applying it to new reactions. But all the ideas and the concepts, nothing new. Two radicals coming together, we learned that in the third week of class. Right? Now we just applying it. Resonance, we learned in the fourth week of class. Took 2 weeks on it, something like that. It it's going to take some work on your part to refresh yourself on those concepts, though. So I wanted to let me go up to this other example because I want you to do this one on your own. And if you bring it tonight to recitation, then we can work through it. Look at the reaction two. We're doing the same exact thing in reaction two. How many allylic sites are there for that molecule?
Would it only be 2?
It's two, right? It's two. It's one here. I agree, and one here. Are you following? But how many
Yeah.
products are we going to get? I want you to
You'll get
think before
4.
you answer. Don't answer until you look at that compound and pay attention to what I'm asking you. How many products are we going to get?
I want to say 4 because of the 2x equation that we did.
Okay, but you sound hesitant. All right. Let me ask this question. Look at the top site with the geminal, the 2 methyl groups on that site. Can I put a bromine there?
No,
Why not?
because they already fulfilled their full octet. They can't really push any more out.
Yeah, it's got a full
Electrons in
octet.
there.
That's very true. All your atoms have a full octet, but is there a hydrogen there that I can abstract in propagation?
Yes.
So there's a hydrogen right here on this atom that already has 4 bonds to
So, okay, I forgot about that.
There's no hydrogen. So
Mhm.
that site is not going to react. In order for you to do allylic bromination, you need a hydrogen at the allylic site that can be abstracted when you get to the propagation step. So here, you're only going to get 2 products. I want you to work on that. We'll talk about it this evening. What time do y'all want to meet and ruin my Friday night?
Earlier.
Russell,
Yes.
It could be earlier.
Yeah.
you able to record this session?
Yeah, I'll record it.
All right, thank you.
Like, what's early? How early?
Honestly, my last class is at 12, but I'm sure y'all have class. But
Yeah, I got
what
meetings,
about
class. I got a bunch of crap.
Like,
what about
I don't
3?
know. I guess 4 is like 4 or 3 are like the earliest for me. Unless you guys, 6 o'clock is fine. But if y'all want it earlier, it doesn't really matter.
Yeah, just it's whatever works for you, Dr. Russell. We'll just adjust.
Really.
All right. We'll do it. Let's just say 5. Let's meet in the middle. Say 5 o'clock.
Okay, that's fine.
I'll record it because we need some work. Hopefully y'all are watching those the videos that I'm sending because that's also going to help. You got to do one or the other. I say this every semester or both. You got to watch the videos and read the sections in the chapter that are outlined in the syllabus, but you can't do neither and think that it's going to fly. It's not going to fly. You got to do something. So we'll meet at 5 today. I'm gonna put a reminder on my phone so I don't forget. But we'll meet at 5 o'clock today.
Dr. Russell, if we're struggling with this concept right here, okay, so I know just watching the videos, usually when I watch them, I have to read the book first in order to understand what you're talking about. But do you have any like YouTube channels that I could look on to figure out and better understand what's going on?
I can find you. I'll tell you what. In the syllabus, there's a link to a website, the Master Organic Chemistry website.
Mm-hmm.
You can look at that as an additional resource.
Okay, sounds good.
Yeah.
Thank you.
Mm-hmm.
I also think Khan Academy has some videos and I think some problems that comes up after.
On the
I'm
Lily
not really sure if
Bromination.
it's on this one specifically, but if you look it up, I'm pretty sure something will come up with that specific topic.
Yeah.
Okay, thanks.
Thanks, Dr. Russell.
All right. I'll see y'all on at I'm about to say on Monday. I'll see y'all at 5. Those of you who can make it. It's not mandatory. So
Okay, thank you.
all right. Y'all have a good Friday.
You too.
All right.
Dr. Russell, I
Yeah.
have a question.
Go ahead.
It's pertaining to makers, but I know we have a meeting tonight at 6.